Welcome students. In the last session, we have overviewed on various concepts in gaseous state such as postulates of kinetic gas theory, derivation of kinetic gas equation followed by the deviation of real gases from ideal behavior. In this class, we will be discussing on van der Waals equation of state for real gases, Andrews isotherms for carbon dioxide, critical constants of gas and the derivation of boil temperature. We came to understand in the last session that it is necessary to apply suitable corrections to the ideal gas equation so as to make it applicable to real gases. We have the ideal gas equation as PV is equal to nRT for n moles of gas, where P is the pressure, V is the volume, R is a real gas constant and T is the temperature. Actually, a number of equations of state have been suggested to describe the P-V-T relationship in real gases. The earliest and the best known equation is that of van der Waals equation. It is in 1873 van der Waals proposed his famous equation of state of a real gas, that is imperfect gas. He modified the ideal gas equation by suggesting that the gas molecules were not mass points but behave like rigid spheres having a certain diameter, and there exist intermolecular forces of attraction between them. The two correction terms introduced by van der Waals are correction due to volume of the gas and the second one is correction due to intermolecular forces of attraction. First, we shall look into the correction due to volume of gas molecules. The ideal gas equation PV is equal to nRT is derived on the assumption that the gas molecules are mass points, that is, they do not have finite volume. Van der Waals abandoned this assumption and suggested that a correction term Nb is required and that should be subtracted from the total volume V in order to get the ideal volume, which is compressible. In order to understand the meaning of the correction term Nb, let us now consider two gas molecules as unpenetrable and incompressible spheres, each of which has a diameter d as seen in the figure. It is evident that the centers of the two spheres cannot approach each other closely than the distance d. For this pair of molecules, therefore, a sphere of radius d and hence of volume 4 by 3 pi d cube constitute what is known as excluded volume. The excluded volume per molecule is thus half the above volume, that is equal to 2 by 3 pi d cube. The actual volume of one gas molecule of radius r is then 4 by 3 pi r cube, which is equal to 4 by 3 pi d by 2 the whole cube, which can be equated to 1 by 6 pi d cube. Therefore, the excluded volume per molecule is equal to 2 by 3 pi d cube, which is equal to 4 into 1 by 6 pi d cube. That means it is the 4 times the actual volume of a gas molecule. The excluded volume per mole of the gas would be then Na into 4 into 4 by 3 pi r cube, where here Na is the Avogadro's number and which can be taken as equal to the correction factor B. The compressible volume per mole of the gas would thus be V minus B. If volume V of the gas contains n moles, then the excluded volume would be Nb. Hence, the ideal volume, which is compressible, would be V minus Nb. The factor B per mole is also known as co-volume. So, van der Waals included this correction term to volume and modified V to V minus B. Now, let us look what does correction due to intermolecular forces of attraction means. In the derivation of the ideal gas equation, it was assumed that there are no intermolecular forces of attraction. Actually, it is not so. In order to take into account the effect of intermolecular forces of attraction, let us consider a molecule which is lying somewhere in the middle of a vessel as shown in the figure. As you can see, it is being attracted uniformly on all sides by the neighboring molecules. These forces neutralize one another and there is no resultant attractive force on the molecule. However, As the molecule approaches the wall of the vessel, it experiences attractive forces from the bulk of the molecule behind it. Hence, it will strike the wall with a lower velocity and will exert a lower pressure than it would be if otherwise. And there was no force of attraction for this particular molecule. It is therefore necessary to add a certain correction factor P to the pressure of the gas in order to get the ideal pressure. The corrected pressure therefore should be P plus the corrected factor P. We shall look how this correction factor P is calculated. The force of attraction exerted on a single molecule is about to strike the wall evidently depends upon the number of molecules per unit volume in the bulk of the gas. That is, it depends directly upon the density of the gas. Further, the number of molecules striking the wall at any given instant also depends directly upon the density of the gas. Thus, the total attractive pull on the molecule which accounts for P is proportional to the square of the density rho. That is, P is proportional to rho square. But density is inversely proportional to the volume, and if V is the volume occupied by 1 mole of the gas, the value of P for 1 volume of a gas will be inversely proportional to the square of volume. Hence, P can be related to 1 by V square, which is equal to A by V square, where A is a constant depending upon the nature of the gas. The pressure correction factor P is also called the internal pressure of the gas. Now, we can write the kinetic gas equation for 1 mole of a real gas including these two correction terms to it. Therefore, it takes the form P plus A divided by Vm square into Vm minus B equal to RT, where A and B are the correction terms. This is known as the van der Waals equation. The constants A and B are known as the van der Waals constant, and these are the characteristic of each gas. This equation is valid for 1 mole of a gas only. If there are n moles of gas occupying the volume V, then as illustrated above, the excluded volume will be given by Nb and the compressible volume will be V minus Nb. The pressure correction factor P for n moles will now be proportional to n square rho square, that is, P is proportional to n square rho square, that is proportional to n square into 1 by V square, which is equal to n square A by V square. Hence, the van der Waals equation for n moles of a real gas becomes P plus n square A divided by V square into V minus Nb, which is equal to nRT. This equation is more accurate than the ideal gas equation, that is PV is equal to nRT, for expressing the relation between pressure, volume and temperature of real gases. Okay, so now we are in a position to discuss the departure of real gases from ideal behavior at different pressures and temperatures as depicted in this picture. In the first case, when the pressure is not very high, the volume V1 will be sufficiently large and the term B may be ignored in comparison. The van der Waals equation for 1 mole of a gas thus becomes P plus A divided by Vm square into Vm, which is equal to RT. That means we can rearrange the equation as PVm plus A divided by Vm, which is equal to RT, and PVm is equal to RT minus A divided by Vm. Thus, the product PV is less than RT by an amount equal to A by Vm. As pressure increases, V decreases and A by Vm increases, and therefore, PVm becomes smaller and smaller. This explains the dip in the isotherms of most of the gases as shown in the figure for carbon monoxide, methane and ammonia, etc. Now, the next case, when the pressure is considerably high, the volume V will be quite small. Now, it may be possible to ignore the term B, but as P is quite high, the pressure correction factor A by Vm may become negligible in comparison with P in the real gas equation. Therefore, reduces to PVm minus B equal to RT, that is PVm is equal to RT minus PB. Thus, PV is now greater than RT by an amount equal to PB. As the pressure increases, the product PB increases and therefore PVM increases. This explains why the value of PVM after reaching a minimum increases with further increase of pressure. We have already discussed that at ordinary temperatures, while the effect of the term A by Vm square is predominant at low pressures, that of PB is predominant at high pressures. At some intermediate range of pressure, therefore, the two effects balance each other. In this range of pressure, the gas shows the ideal behavior. This explains the existence of a small horizontal portion in the isotherms of gases like carbon monoxide and methane as seen in the figure. The third case is considering when the temperature is high. If at a given pressure the temperature is considerably high and the volume will become sufficiently large to make the value of A by V negligibly small. At high temperature, B may be also negligible in comparison to V, which is now sufficiently large. Under the conditions, the van der Waals equation approaches the ideal gas equation PV equal to RT, and this explains why the deviations become less at high temperatures as seen in the figure. So, we should correctly substitute the conditions of temperature and pressure so as to apply the van der Waals equation to our gaseous system under study. Now, we shall discuss on the boil temperature. As already mentioned by me in the last session, the temperature at which a real gas obeys Boyle's law is known as the boil temperature, which is represented as Tb. Mathematically, boil temperature is a temperature at which limit P tends to 0, dou Pv by dou P at constant T is equal to 0. That is, we can write the van der Waals equation as P plus A divided by V square into V minus B, which is equal to nRT. Rearranging this van der Waals equation, we can write it as P is equal to RT divided by V minus B minus A divided by V square, or PV is equal to RTV divided by V minus B minus A divided by V. At boil temperature, T is equal to Tb. The ideal gas equation becomes PV is equal to RTB. That is, we can write RTB is equal to RTBV divided by V minus B into A by V. That is, rearranging RTBV divided by V minus B minus RTB is equal to A by V, or RTB into V divided by V minus B minus 1 is equal to A by V. That is, RTB into V minus V plus B divided by V minus V is equal to A by V, or more correctly RTB P divided by V minus B is equal to A divided by V. That is, Tb is equal to A by V into V minus B divided by Br is equal to A by Br, as B is small. That is, we get the final relation for Boyle's temperature as Tb is equal to A divided by Br. Now, let us discuss on the critical constants of a gas. The most characteristic property of gases is that their molecules lie far apart from one another and are in continuous rapid motion. Each molecule therefore leads almost an independent existence. This is particularly so when the temperature is high and pressure is low. However, as the temperature of a gas is lowered, the kinetic energy of the molecule decreases, isn't it? The volume occupied by the gas then decreases. At a sufficiently low temperature, some of the slow moving molecules cannot resist this force of attraction and they come closer and closer, and ultimately the gas changes into the liquid state. Thus, liquefaction of the gas results from this degrees of temperature. Increase of pressure has also the effect of bringing the gaseous molecules closer and closer to one another due to decrease in volume. This is an additional helpful factor in converting a gas into liquid. Thus, increase of pressure and decrease of temperature both tend to cause liquefaction of gases. The effect of temperature, however, is more important than that of the pressure, because for each gas there is a certain temperature above which it cannot be liquefied no matter how high a pressure may be applied. This temperature is known as the critical temperature. Thus, The critical temperature of a gas may be defined as a temperature above which it cannot be liquefied, however high the pressure may be. At the critical temperature, a certain pressure is needed to liquefy the gas, and this pressure is called the critical pressure. Now we shall move to the discussion on PV isotherms of carbon dioxide. It is otherwise known as Andrews adsorption isotherm. The importance of critical temperature of a gas was first discovered by T. Andrews in his experiments on pressure-volume relationships, that is isotherms, for carbon dioxide gas at a series of temperatures. The isotherms of carbon dioxide determined by him at different temperatures are shown in this figure. Let us now consider first the isotherm at the lowest temperature, that is 13.1 degrees Celsius. The point A represents carbon dioxide in the gaseous state occupying that diminishes as a certain volume under a certain pressure. On increasing its volume, the pressure, that is the curve AB, at B, which represents a pressure of 49.8 atmosphere, liquefaction of the gas commences, and thereafter a rapid decrease in volume takes place at the same pressure as more and more of the gas is converted into liquid state. At C, the gas has become completely liquefied. Now, as the liquid is only slightly compressible, further increase of pressure produces only a very small decrease in volume. This is shown by a steep line CD, which is almost vertical. Thus, along the curve AB, carbon dioxide exists as a gas. Along BC, it exists partly as gas and partly as liquid, while along CD, it exists entirely as a liquid. It may also be noted that a considerable decrease of volume represented by BC takes place when at a constant pressure. Now, the isotherm EFGH at 21.5 degrees Celsius shows a similar behavior, except that now the liquefaction commences at a higher pressure and the horizontal portion FG representing degrees in volume becomes smaller. At still higher temperatures, the horizontal portion of the curve becomes shorter and shorter until at 31.1 degrees Celsius, and it reduces just to a point as represented by X. At this temperature, therefore, the gas passes into a liquid state gradually. Above 31.1 degrees Celsius, the isotherm is said to be continuous. There is no evidence of liquefaction at all. Andrews thus concluded that if the temperature of carbon dioxide is above 31.1 degrees Celsius, it cannot be liquefied, no matter how high the pressure may be. He called 31.1 degrees Celsius as the critical temperature of carbon dioxide. Since then, other gases have been found to behave similarly. There is no fundamental difference between the so-called permanent gases such as hydrogen, oxygen, nitrogen, etc. and the temporary gases such as carbon dioxide, chlorine, hydrochloric acid, ammonia, etc. The difference lies in the fact that while the so-called permanent gases, they have very low critical temperatures much below the ordinary range of temperature, and the so-called temporary gases have critical temperatures well within the range of ordinary temperatures. Finally, in this session, we shall familiarize the law of corresponding states or the principle of corresponding states. In 1881, Van der Waals showed that if the pressure, volume and temperature of a gas are expressed in terms of its critical pressure, critical volume and critical temperature, we can obtain an important generalization called the principle of corresponding state. That is, we can write P divided by Pc is equal to Pr, or T divided by Tc is equal to Tr, or V divided by Vc equal to Vr. Here Pc, Tc and Vc are critical pressure, critical temperature and critical volume, and Pr, Tr and Vr are called the reduced pressure, reduced volume and reduced temperature respectively. Substituting this in the Van der Waals equation for 1 mole of a gas, that is P plus A divided by Vm square into Vm minus B equal to RT, and through subsequent solving we finally get this relation as Pr plus 3 divided by Vr square the whole into 3 Vr minus 1, which is equal to 8 Tr. And Looking on this equation, we can clearly see that it involves neither R nor the van der Waals constant A and B. Hence, we can apply this equation generally to all substances under study. It follows from this equation that if two or more substances have the reduced temperature and the same reduced pressure, they would have the same reduced volume, and this statement is known as the principle of corresponding states. That is, more clearly, two or more substances having the same reduced temperature and the same reduced pressure, thus having the same reduced volume, are said to be in corresponding states. Thus, summarizing this session, we have discussed on van der Waals equation of state for real gases, Andrews isotherms for carbon dioxide, critical constants of gas, and finally, the principle of corresponding states. In the next session, I will be talking on Maxwell's distribution of molecular velocities and energies, its derivation and graphical representation, and the experimental verification. Hope so far the concepts are clear to you. Thank you, students.